This lecture is entitled Opposites Attract, and in the immortal words of Paula Abdul, I take 2 steps forward, 2 steps back. We come together because opposites attract. And so the purpose of this lecture is to introduce you to the ideas of opposites attracting via something called Coulomb's law. So the goals for this presentation are that students be able to graphically and algebraically, that's a big one, algebraically demonstrate the effect of a different variable on Coulomb's law. You should be able to draw an electric field and predict the motion of a charged particle in a field, and you should be able to use the equation F equals K Q1 Q2 over D squared to figure out any of the other variables. You should also be able to calculate the magnitude of an electric field and the resulting force at any point. That's going to be considered an extension that we're going to get to, but it is a really important idea. So, what we already know. We already know that there's two types of charge. You have a positive charge and you have a negative charge. Now we know that you can take a neutral object and you can turn it into a positive charge, or you can take a neutral object and you can turn it into a negative charge. We call that charge transfer. Now we also know that charge is conserved in a closed system. So if you close this off from the rest of the world, you have to have a set amount of charge. You can't change it. So that's stuff that we already knew. Now let's take a look at what we learned in the lab. We learned in the lab that when we increase the charge, we increase the force. So if we take this value and we increase the charge, we increase the resulting force between the charges. And we also learned that if we increase the distance between the charges, so we move the charge out here, we end up decreasing the force. We also learned that the orientation of the charge, that is whether it's a positive or a negative, plays a big role in determining whether or not the force is attractive or repulsive. In this case, you have two positive charges, and you see that the forces are pushing away from each other. If you had a positive and negative, they ended up attracting each other. And that leads us to our first thing that we're going to talk about is the fundamental law of static electricity. And that is that opposites attract and like charges repel. So if you have two charges that are the same, they will push away from each other. If you have two charges that are opposite, they will attract to one another. It doesn't matter if it's two positives or two negatives, the result will be the same. If the charge is the same orientation, they will repel away from each other. We start off looking at Robert Boyle. Robert Boyle is famous for his idea of Boyle's law that was studied in chemistry, but he was also one of the first people to record the attraction and repulsion of electric forces. Some people had seen that it attracted, but the idea of a force attracting and repelling was kind of interesting because people only knew that gravity could attract. They didn't think that gravity could repel, and it can't. So this is kind of an interesting idea, the fact that an electric force can attract and repel depending on the circumstances. That led to the work of Joseph Priestley. Joseph Priestley was a famous priest slash philosopher who was very famous because he was the first one to isolate oxygen from air before people just thought of air as being air instead of having different components in it. So Joseph Priestley was the first one to kind of say, okay, well, there's other stuff in there, and I've actually isolated oxygen, which is crucial to human survival. So he's really famous in chemistry, but also he's real famous in physics because he was able to predict the fact that the electric force would be an inverse square law. And it's very similar to gravity. Remember when we talked about gravity, we said F equals G m1 m2 over d squared. And we said that increasing the distance decreases the force by a lot. Well, Joseph Priestley predicted the same thing for the electrostatic force. Then we come to George Augustin Coulomb, and he's who we have Coulomb's law named for. He's this, great guy holding this scientific instrument. It's a great portrait that you have there. He was able to describe the relationship between charge, force, and distance, and he did that with what we now know as Coulomb's law. And Coulomb's law is F equals K Q1 Q2 over d squared. In essence, he said, if you take the charge and you double the charge, you double the force. There's a direct relationship there. He also said that if you double the distance, you quarter the force, once again taking on the idea of Joseph Priestley's inverse square law. So if I'm doubling the distance, I end up 1/4ing the force because of the fact that this is an inverse square law. So now let's take a look at some examples. The first one says that you have two charges that are separated by a distance d, and it provides a force of F. So we've got a force of F. The next thing we say says, if you increase the magnitude of the charges to 3 times and 5 times respectively what they were, what is the new value of F? But it says we also double the distance. So we're doing 3 things. So I can represent the first value as just F. Now, if I were to just increase the magnitude of the first charge, the force would go up by a factor of 3 because I increased the charge by a factor of 3. If I were to increase the charge of the second one by a factor of 5, I would have to increase this by 5 as well, and all of a sudden, if I was just increasing the charge by 3 and 5, you would expect a 15 times the force value. But you have to account for the doubling of the distance as well. Now remember, doubling the distance, okay, if you double the distance, that is an inverse square law. So you're actually quartering the force. So you've got to put these things together. If I multiply the force by 15 and I quarter the force, the resulting total force of this thing would be 15 over 4, which is 3.75. So even though you're increasing the magnitude of the force by quite a bit, because of the fact that you're simultaneously manipulating the distance, the overall effect is not nearly as much. You have this idea that it's just 3.75 times larger. In this one it says, which graph best represents the relationship between electrostatic force and distance? And this one is, if you were looking at it in terms of distance, distance is an inverse square law. So what that's saying is, as distance goes up, force goes down by a squared amount. Okay, the fact that it's a squared amount right there means that I have to have a curve in my graph. So you can eliminate these right here, because the square value means you've got to have some sort of curve, some sort of quadratic. Now the fact that if you look at it, this one says that as distance goes up, force goes up. And that's the exact opposite of what happens. As distance goes up, force goes down. So this is the correct graph. You need to understand the relationship between all of these variables. The next one says you have an electron and you want to know what the path of the particle will be. So if you're firing this thing, it's going to be right here. And then all of a sudden it's going to be attracted to the positive end and it's going to be repelled from the negative end, meaning it's going to move slightly in that direction. And it's going to move slightly in that direction and slightly in that direction and so on and so on and so on and so on and so on. Now if you look at this, it appears like it's in a straight line because I didn't do a great job, but really the object is accelerating towards that. Well, how do you know it's accelerating? Because it's attracted to it, we say that that's a force. Remember, anytime you have a force, there's an acceleration. So really, if you were to look at it, it would be something like this, where it curves upward, where it looks almost like a straight line at the beginning, and then all of a sudden it starts to curve and curve and curve more. Okay? Next we have the idea of Coulomb's law. Coulomb's law is F electric is equal to Kc Q1 Q2 over d squared. Now sometimes you see it in different forms. Sometimes this d is called r, and a lot of times you'll see this k is just k instead of not Kc, and almost no one puts this electric on here. But I wanted you to see this force right here because this is how it's written on the tax formula chart, excuse me, the star formula chart. So if you were to take a look at this, this is generally available to you, so you need to be aware of it in this particular form. So the first thing you need to look at is the electrostatic force. The electrostatic force is a force that's the same as all the other forces we've covered. The only difference is the reason why you have a force here is because of charged objects. It can still be measured with a spring scale or a force meter. Everything else is the same. The Kc value is new as well. You have Coulomb's constant, and that's where the constant is very similar to the G value when we talked about gravitational force, in the fact that it turned a proportionality into an equality. Now the difference between this and the G value is this is a very, very, very large number, and it indicates just how strong the electrostatic force is. If you were to compare that to the G value, remember G is 6.67 times 10 to the minus 11th, which is much, much, much smaller. So you can say overall that the electrostatic force is stronger than the gravitational force just based solely on that constant value. Next you have Q1 and Q2. We talked about those in the previous lecture. That's just the amount of charge. And then finally you have the distance value, which we've talked about quite a bit. The only thing that's really important is that the distance has to be measured between the centers of mass. So if you were to look at it, if I have these two charges, this is not the distance. Instead, what you have is this would be the distance. Okay, so that's the distance right there. You have to account it from a center of mass to a center of mass. So now, if we take a look at some examples, this is the B1 example, and this one is about as tough as it gets. So don't be discouraged if you have problems with this first one, because this is pretty tough. It says determine where a single electron can be placed between the two charges, resulting in no movement of the electrons. Okay, so here's what you've got to do. I got to put the electron in here, and the best idea for it to be is in between the two charges. You'll see there's actually a couple of different answers a little bit later. But once you do this, you say, okay, I'm going to put this electron right here, and what I want to happen is the attraction of the electron to this positive charge equals the attraction to this positive charge, thereby canceling each other out. Remember, we call that, when the forces equal zero, we call that equilibrium. Okay, so the whole idea is to get to equilibrium. And if you look, we can go ahead and set up an equation. We can say F equals F. Okay, so the two electrostatic forces have to equal each other, or another way of saying that would be K Q1 Q2 over D squared equals K Q2 Q3 over, we're going to call it D prime squared. The prime is just to indicate that these are different distances. This is going to be distance, and this is going to be D prime. It's like saying D1 and D2. So now if you notice, you actually have some common things in each one of these. If you notice, you're doing this as an equality. You have K in both sides, so that'll cancel out. You have Q2, which is the value of the electron, in both sides, and it cancels out. So now you've kind of taken this thing and you've knocked it down a little bit so you can start to kind of deal with it. So now we have Q1, which is 2 times 10 to the minus 6th over D squared. I still have no idea what D squared is. And then on the other side, you have 12 times 10 to the minus 6th. But then instead of writing D prime squared, what I'm going to do is I'm going to do something a little bit different. I'm going to say that if this is D and the whole thing is 2, that I can represent this as 2 minus D squared. By doing that, what I've done is I've eliminated a second variable. Instead of having to do with D and D prime, now all I have are D's. So now I can cross multiply and I can divide. And when I do that, I'm going to get the number, I'm going to just make a little room right here. I'm going to get the number 12 times 10 to the minus 6th D squared equals 2 times 10 to the minus 6th, and then I'm going to have 2 minus D squared. Now the first thing I'm going to do is I'm going to divide both sides by this 2 times 10 to the minus 6 number. It's going to make my life a little bit easier. You're going to see some stuff rearranged a little bit different. And when I do that, I get 6 D squared equals, and then this term is gone now. So what I have now is 2 minus D squared. And what you should realize is that's a quadratic equation at this point. So now you can say 4 minus 4D plus D squared. When you do that, now you have a quadratic equation that you can deal with. At this point, I'm going to change colors just to show you that I'm doing the math now. And I can say, move the D over, I have 5D squared plus 4D equals, minus 4 equals 0. At this point, you can do the quadratic formula. The quadratic formula is going to be, you have an A term, you have a B term, and you have a C term. So you do x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. You should be familiar with that from math. If you're having struggles with that, make note of it and ask your teacher to work it out for you when you get to class. But you should be able to say that whenever you do this, the d value has two possible values. The first one is minus 1.38 meters. Okay, what that means is that I can actually put it right there. So I can put it to the left of the actual system, which is interesting because you have to deal with the repulsion of these two things, but that'll work. If you were to put it negative 1.38 meters here, the system will actually reach equilibrium. Another option is if you put it in between, but when you put it in between, you get a value of 0.58. So which one is correct? Well, they both are. So this is a tough example. So if you were to look at this and struggle, stay with me as we work through some more examples, because we're going to work some more examples as we go through. This one says determine the radius that a single electron orbits a helium nucleus if it has been determined that 2.5 times 10 to the minus 8th newtons is required to hold the electron in orbit. Okay, so in other words, I'm saying that in order for this to exist, there is a force of 2.5 times 10 to the negative 8th newtons. In addition to that, I have Q1. You maybe say, I don't know what Q1 is. Remember, we talked about the charge of an electron. So this would be minus 1.6 times 10 to the negative 19th. Q2 would be positive 3.2 times 10 to the negative 19th. And you are trying to solve for the distance between them. Remember, the K value is always a constant. It's that 8.99 times 10 to the 9th. At this point, you just have to plug everything in to the equation. F equals K Q1 Q2 over D squared. So if you look, this example is much easier than the previous one because you're just plugging things in at this point. So what you would do is you would say 8.99 times 10 to the 9th times 1.6 times 10 to the negative 19th, and we need to make that negative, times 3.2 times 10 to the negative 19th, divided by D squared equals, remember it's equals, and then we have this 2.58 times 10 to the minus 8th number. Okay, what you're going to end up having to do is you're going to have to move the D squared over here, and you're going to move this 2.5 times 10 to the minus 8th back under here. Okay, it's algebraic rearrangement. When you do that, now you have D squared equals a number. You can enter this number into a calculator. Once you do that, you need to remember that that's a D squared value. So in order for you to get the actual number, you need to take the square root. And when you do that, you get the distance is about 1.36 times 10 to the minus 10th, which is pretty close to the actual radius for an electron orbiting a nucleus. Okay, next it says determine the distance between two charges, 1 times 10 to the minus 4th and minus 5 times 10 to the minus 5th, if they are subjected to 1 Newton of force between them. So this is a very similar question to the one that we just did. You have a value of Q1, you have a value of Q2, and then you have the force that's between them. So you're going to use the equation F equals K Q1 Q2 over D squared. And when you do that, you're going to plug in, you're going to say 1 Newton of force. And people usually kind of have issues at this point because they say, how can I have 1 Newton of force whenever there's a positive and a negative charge? You're right, this 1 Newton of force is the magnitude of force. So it should really be a minus 1 there. And that equals 8.99 times 10 to the 9th times, and then at this point you plug in your charge values. 1 times 10 to the minus 4th, minus 5 times 10 to the minus 5th, divided by D squared. Change these two values. Change those two values right there, and when you do that, you get this is equal to D squared, and by dividing by the negative 1, all you're really doing is changing that into a positive. You can now put this thing in your calculator, take the square root of it, and when you do, you get a distance is about 6.7 meters. Alright, in example B4, it says that you have determined the force between two 1 microcoulomb charges separated by a distance of 15 meters. One of the things that you should realize is that a charge value, 1 coulomb, is a very large charge value. Actual charges tend to be dealt with in micro and nano coulombs, sometimes millicoulombs, but smaller values than a full coulomb of charge. If you were to go ahead and look at this, 1 microcoulomb is the same thing as saying 1 times 10 to the minus 6th coulombs. So once you know that, you can plug it in. You can say F equals K Q1 Q2 over D squared. Or you have your Q1 and your Q2, and you have your D. So you plug in. You say equals 8.99 times 10 to the 9th. I'm going to do a little bit of a trick here in saying 1 times 10 to the minus 6th and then squared, because 1 times 10 to the minus 6 times 1 times 10 to the minus 6 is the same thing as 1 times 10 to the minus 6 squared. Take that, divided by the distance, which is 15, but remember the distance is a squared term. You would put this in your calculator, and when you do this in your calculator, you should get a value of about 4 times 10 to the negative fifth. Actually like 3.9996, but it's about 4 times 10 to the minus fifth newtons. There are numerous applications of Coulomb's law, and the first would be like the idea of electroplating. Whenever you're taking something and you need to cover it with a metal, a lot of times it happens with gold plating, but there's lots of other things you do it. What you do is you generate a charge, and whenever you generate a charge, you can create an oppositely charged metal ion that will fly to it. Because of the differences in the charges, they'll be attracted to one another. That's a way that you can get a very, very thin layer of gold plating, which gets the effects of having gold, but at the same time costs much, much, much less. Another one is the idea of the electronic signature pad. Whenever you have an electronic signature pad, okay, some of them are hooked up where they have a positive or a negative charge. These aren't always the case, but it's true in most grocery stores. You have a positively charged pen, and then you have negatively charged ink capsules. And whenever you place the positively charged pen onto the surface, it actually pulls these negatively charged ink capsules. They're not really ink, but they pull these capsules up to the top so you can actually see what it looks like whenever you write on the surface. Okay, so that's what you look at when you look at an electronic signature pad. Another one would be the idea of the normal force. We said that the normal force is the force that's exerted based on the interaction between any object with its surface. If you look at the ultimate outside layer of any matter, you have atoms. And in that atom, you have a proton, and on the very outside, you have an electron. And if you look at it, you could have a proton here with an electron, and then the surface that you are resting on has a proton, and then it has an electron. The normal force is the interaction of these two electrons, or the electrons in the outer layer of something interacting with the outer layer of another. It's a repulsive force, and so that's where this upward force due to the surface of a table or a ramp comes from, is the idea of the electrons repelling each other. Now, Robert Millikan actually used this idea of Coulomb's law and the interaction between positive and negative charges to measure the charge of an electron. This is a feat it's really interesting, and it's astounding that he was able to do this with the technology that he had, but he ended up winning the Nobel Prize. He was also famous for measuring Planck's constant, which we'll talk about. You should have been exposed to Planck's constant a little bit in chemistry, but we'll talk about that a little bit later. The Millikan experiment was he took oil droplets, and these oil droplets he would spray into a very, very fine mist, and they would become charged because he would put an electric charge on them, and he was able to suspend them between two plates. He had a positively charged plate, and he had a negatively charged plate, and he was able to adjust these, and when he adjusted them, he was able to get an oil droplet to levitate. And based on the fact of how small he could make the oil droplets and the minimum difference that he had to do to adjust the plates, he was able to infer that the charge of an electron was 1.6 times 10 to the negative 19th coulombs, which is the value that we now use in this class. Now, the idea of the electrostatic force is interesting, but you also need to look at the idea of an electric field. An electric field is kind of a map of what is going on in terms of the forces. So it's always drawn from the positive charge to the negative charge. That's convention. There's no particular reason other than the fact that this is what they do. Well, actually, there is a reason. The reason is whenever you draw these lines, you're saying what would happen if I put a positive charge there. And if you put a positive charge right here, you would expect that positive charge to follow this line and move towards the negative charge. So that's the idea behind an electric field. Now, there is also something called electric potential energy, and that's the idea that charges will move based on the magnitude and orientation of their charge. So if you were to look, if I take a book and I hold it over the surface some height, like 2 meters above the ground, the book is said to have gravitational potential energy because it has the ability to fall when it's released. You have the same thing with charges. If I have this charge right here, and I have this charge right here, they have the potential to move towards one another, but they're being held constant. So we say that they have electric potential energy. The work, remember work, that is necessary to move it to this position is equal to the electric potential energy that's stored. That's just another statement of the law of conservation of energy. So the idea that you can take work and you can turn it into electrical energy is going to be very useful when we start to look at things like electromagnetism. In this example, it says draw the electric field resulting from the charges below. Now realize that the closer that two charges are together, the more they're going to interact, the more lines there are going to be. So you're going to have a great deal of lines here because these charges are very close together, so they're going to have a very, very strong electric field. Now these are not as close together, so you're going to have kind of the same thing going on. You're not going to have as many lines because it's nowhere near the force that you have between the other two. So this is an example of the electric field that you have for these particular charges. The next example says, okay, take that same idea, the idea of electric charges, but now I also want to know what would happen if I put a proton somewhere in there. So the idea is you still have this electric field right here. They're kind of far apart, so it's not a terribly dense electric field, but I can draw some lines that are there. And now what happens if I were to put a proton here? Well, if you put a proton here, it would follow this line. It would initially be kind of pushed away from this proton, and then it would be attracted to this electron. So it gets to be really interesting when you take electric field lines that go like this, because of the nature of the charges, and you can actually put a proton right here, and it will be repelled away, circle back around, and follow the line and be attracted to the negative end. Alright, this is an extension on the electric field. It's incorporating a formula into what we actually have. Now the formula for an electric field is the idea of E equaling F divided by Q. It's the whole idea of the electric field is, what if I take a charge and put it here? What kind of force is exerted on it? So you have this formula E equals FQ, but a lot of times you will see Coulomb's law plugged in for F. And when you do, it simplifies Coulomb's law to this, which is basically the same formula, but the second charge value is missing. So depending on the circumstances that you have, you can use either one of these particular equations. Now the only thing that's new in this particular formula is the idea of the electric field. And we've talked about that. It's a map. It's kind of a if you took a look at it, it's like one of those elevation maps where it shows you the elevation on a flat surface. It's the same idea for an electric field. It's showing you the force in kind of a two-dimensional outlook. Now the units for the electric field are newtons per coulomb. Sometimes you see some other things, but we're not going to get into those in this particular class. So it says determine the magnitude of an electric field produced by a single proton at the Bohr radius. So we're talking about an extremely small distance right here, because you're looking at what is the force that is produced, or what is the electric field produced by basically a hydrogen atom. So we have the idea that E equals F divided by Q. Now I don't have F. I do have a Q value, but I don't have the force that's exerted on it. Now I could do that, but let's go ahead and take a look at the other formula. The other formula was the idea of E equaling E equaling K Q1 divided by D squared. And I do have that. So the question is which charge do I use? Do I use the positive or the negative charge in this particular case? You're looking at the electric field that's produced by a proton. So you're going to use the proton value as this particular charge. And generally speaking, you're looking at the positive charge when you're looking at an electric field. So we would say equals 8.99 times 10 to the 9th times 1.6 times 10 to the negative 19th. Divided by, and we have our d squared value. Now our d is an extremely small value, so when you take that value and you're dividing by a small value squared, you end up getting a very, very large value for the electric field in this particular case. The electric field, you would say, would be about 5.14 times 10 to the 11th newtons per coulomb whenever you divide that out, which is an extremely small value, or excuse me, it's an extremely powerful electric field. So now let's take a look at another example. In this one it says determine the magnitude of the electric field responsible for exerting a force of 100 newtons on a 1 nanocoulomb charge. That's what the NC stands for. So you're going to take a look at this and you say, if I use the formula E equals F over Q, I have everything. I have an F and I have a Q value. So that allows me to use this particular formula. Or, in our case, it would be E equals 100 divided by 1 nanocoulomb. Now 1 nanocoulomb is 1 times 10 to the negative ninth. 100 divided by 1 times 10 to the negative ninth ends up giving you a value of about 1 times 10 to the 11th newtons per coulomb. Once again, an extremely large value for an electric field. The last part of this particular formula or this lecture is the extension for the EPE formula. Sometimes you need to take a look at the electric potential energy, or P electric. Now remember, we said that the electric potential energy is equal to the work that is done in moving the charge there. And work, we already learned, is force times distance. So you have this idea that the electric force, or excuse me, the electric potential is equal to FD. Well, another way of saying that would be QED, because remember E equals F over Q. Okay, if you rearrange that, you get F is equal to QE, and that's where we get the idea of QED. Another one is if you were to take this and substitute Coulomb's law in for the force, you get K Q1 Q2, and then it's over D instead of over D squared. So either of these formulas, any of these formulas, is useful depending on the situation. So let's take a look at a situation. It says a force of 10 newtons is exerted on a proton over 10 meters. What is the change in electric potential energy? Well, work is equal to force times distance. I have a force, I have a distance, and it's as simple as that. Work is equal to 10 times 10, which is 100 joules. Now they're not always that easy. You've got to look and see what's there. So now we look at the next one. It says, how much work should be done on a proton to place it 5 millimeters away from a 1 coulomb charge in a 15 newton per coulomb field? So we have the idea of work is equal to force times distance. In this case, this won't work because I don't have a force. I do have a distance, but I don't have a force. So I go to the next one and I say QED. And if you look, I have Q, I have E, and I still have D. So in this case, I would say 1 coulomb charge times a 15 newton per coulomb field times 0.005. Whenever you multiply all those things out, you get a very small value of about 0.0075 joules. So there's a lot going on in this particular lecture. There's formulas for electric potential energy and electric fields, but by far the most important one for you moving forward is the idea of Coulomb's law. You have to understand Coulomb's law.